Well, hello. It's higher tier lesson. It's Thursday, and I'm going to try and do some teaching. I've been working hard all day trying to get different lessons covered, and today you've tuned in, hopefully, all three of you that are here now, but hopefully we'll get some more, and obviously this stream stays up, so I'm designing it so it's helpful to certainly all my year 10s and everyone at my school, but anyone who joins in and wants to learn a bit about transforming graphs. This lesson is not going to be the full half an hour. I'm going to start with the higher tier lessons, try and make them punchy and get the information that download to you as quickly as we can, but in a nice way that hopefully makes some sense. Now, what we're going to be doing is we're going to be looking at the ways graphs change, the way graphs can move up and down, the ways graphs can move right and left, the way graphs can get narrower and open more. And to do so, I'm going to go straight in now to working on here. So, hopefully, you can now see me. And I'm in a piece of software called OneNote because it's got some useful stuff, especially for higher tier GCSE and A-level, calculating things out. As you can see, I'm going to start off with the equation y equals x squared. And in doing so, when I highlight it, it allows me to draw around it, and then it identifies that it's to do with maths. So when I click maths, it says it's y equals x squared. I can now select an action, which is to plot it, and we're going to drag this graph onto the page. Now, we want to look at what happens when we do different things. So what better way than to experiment with y equals x squared plus 3? Because by doing this, hopefully, we can not only have me explain it, you can see live exactly what is happening. So we can directly compare what's changed. Well, all that's changed, in fact, is that this graph, which looks very, very similar to this graph, appears to have gone up 3. In fact, if we zoom in and drag it up slightly, we can see it's much the same, but just up 3 spaces. So therefore, adding a 3 there just moves the graph up. Similarly, it's not too difficult for us to see that the same is true when we have y equals x squared minus 3. And we can then, once again, get the graph of this, insert it, and we can see that's gone down 3. So what's going on here? Well, in a graph, when you've got an equation, you have got an input and an output. The y is always your output, and the things you do to x are the input, the machine if you want. You're putting in x, and you are doing some stuff to it, and getting an output. And in this case, the original equation we started with, of y equals x squared, we've then, after getting that amount, added 3 or taken away 3. So therefore, 1 adds 3 and moves all of the outputs up 3. 1 takes y equals x squared and moves all the outputs down 3. What we therefore have got is moving up and down, and we can come up with a rule here. The rule we have is that when you have y equals x squared plus a, you end up with going up a spaces. You can even describe this as a vector change of 0 a. As we know with vectors, if you've done any vectors so far, the top number is how far you move right or left, and the bottom number, which we're calling a because it's an unknown number, is how much you're going up or down. And we would call this a translation, because we are translating, we are moving the entire graph up a spaces. So in this case, the one I did in blue was up and down 3. Now this is not to be confused with if I take my original one, but this time I'm going to change it ever so slightly. So to do so, let's use a slightly different colour and see what happens when we've got y equals x squared. But instead of y equals x squared, let's have x minus 3. So this time we are doing the minus 3 before we do the squared. Y equals x plus 3. Now, if you've not seen this before, some of you will have some ideas. If you have seen it, this is revision, and this is also suitable for A-level students as well. We don't need to have the plus, so I'll just rub that out. So, what are we expecting to happen? Well, some of you may have anticipated this will change it in a slightly different way. Oh, it didn't quite identify it, so I've just got to fix it by rubbing out that. It didn't like the fact that it was a bit too close to there. So if I click on I should be able to move that bracket over and open it up a bit and see what happens. And hopefully it's got an idea now. Right. I'm obviously going to have to get used to writing slightly neater in this. Y equals brackets x minus 3 all squared. It's all a useful learning experience for myself and for you to see quite what you can perform on this software. And we've now got what I wanted. So we'll again plot and we'll insert on the page. And was that what we expected? I can see this whole graph from here originally appears to have moved 3 forwards. But that's a minus. How is it possible that that's a minus and yet it's moved forwards? Well, here's why. The minus 3 has happened to the input, not to the output. And in doing so, it means the input we have got here is 3 earlier than we would expect. So an input of 3 gives us effectively an input of 0. An input of 6 is now an input of 3. Everything is happening later than it should. So we're still getting the same set of outputs, but we're getting them only when x is 3, which means it moves to the right. I guess you can probably work out what that does for the other one we're working with. And I'm not sure, many people are going to be surprised to see that it does the exact same thing, but it moves it left. So if we just quickly draw on here, this is going 3 spaces left. And we can again go to a final rule for this. Y equals x squared. Oh, we're not doing the squared, are we? Y equals x and plus a all squared will make it go to the left a spaces. So it is a translation of minus a 0. It's not going to go up or down at all. Now, near the end of this stream or video, whenever you're watching it, I will mention how we can use the 2 things on this page to... I've got that hidden by the thing. So we need to make sure I hide myself. Hopefully that's done that. Hopefully you can now see the graph that it is... We've got the different graphs on here, and I need to remember to keep that bottom left corner free. So we go on a little bit more. we're now going to talk about what happens when we have got graphs which go and do multiples of the amounts. Hi Sam, I'm going to be doing some 3D trig questions at some point, but it's not down for today for 1:30. So I'll get back to you and try and do things. I'm sorry, Lumi. I'll try. I've tried to remove the screen, but unfortunately, if I can just do this for a second, I will be able to fix that so that it doesn't happen again. But hopefully I've moved down so I won't draw down around that bottom corner anymore. Okay. So we have what happens when we have y equal, we're going to start with a different graph now. Y equals x cubed. Let's see what this is going to do to this graph. So this is what we're starting with. It doesn't like that, does it? Maybe this will be better. Okay, so I wonder if I write it as y equals x cubed that's better. It prefers it like that. So what I'm going to do with that is plot that, and if you're rusty on your graphs, this looks like this. And we can make that a bit bigger so everyone can see what's going on. What we're expecting to do now is what happens if I do this, and instead I'm now writing y equals 2x to the 3, or y equals half x to the 3. So we're now looking at what happens when we have multiples. Remember, we do the x cubed first here. Let's see how good it is at picking up my writing this time. It might do, it might not. It likes it. It's a winner. I just need to learn to write neater, I think. So hopefully you can see this. The thing it's changed is, well, it hasn't changed too much, but that 5, it seems to be going not as steep. Because if we look here, I can show you directly how they're similar. This here is 2. And if I carry that up, way up there, it hasn't reached it. This is 2. If I carry that up, it reaches it there. But 1 reaches at 1. Here, 1 reaches at 2. It's clearly gone stretched that way. We can also look at it here. This is -1. This is -2. It's got stretched. Imagine putting a pin in there and pulling upwards and downwards. It has stretched it, but it's done the opposite of what you'd imagine. It's made it twice as tall both ways, just as you think. It's going to make it twice as tall there, so we can probably predict what's going to happen here. We haven't done any fractions yet. Let's see what happens when we try and do math. Well, it kind of likes it. I'm guessing that I'm supposed to draw my x's a different way, so it knows what I'm talking about. So let's give it one more chance, because why not? You're learning maths. I'm learning how to do this thing, and I want everyone to understand. So what happens if we do? That's not going to be an x, is it? everything I've ever taught my children, like my students, says that you should never be putting X's like that. But I imagine there's a chance it's going to not mind that. There we go. As soon as I do that, yep, happy with that. And there's the plot. And this time, you can see it's actually half as big. It's got taking longer to go up. This one went with the 1, whereas this one for 1 went up to 2. This one for 1 goes up to 4. No, it doesn't. For 2 goes up to 4. This one for 2 went up a long way. So this is up to 8. So it's half as high again. So we can see that it's going half the height. What's effectively happened is it has been squashed. Possibly should have done this at some point. Sorry, Sam. Sorry, everyone who's watching. We'll get there eventually. This is all the stuff I've been describing. What a nightmare. So, you can see here we've got y equals x cubed, and we've got y equals 2x cubed, and y equals half x cubed. And you can see this one on the left has been squashed, and the one on the right has been stretched apart, and this one on the right has been sort of squashed together. It's meant 2 times smaller, and this one's 2 times bigger. And we call this a stretch scale factor 2. So far, we've seen that if you have a number multiplied by the x cubed, it stretches it, and half it scrumples it together. If you have the numbers inside a bracket, it goes left or right. And if you've got a number outside the bracket, it goes up or down. So what's the reason I'm doing this? Well, we're going to do one more lot just of what happens when we have y equals minus x cubed. So what is happening to y equals minus x cubed? Well, what that does is it flips the graph round. Everything that was going up on the right and down on the left is now going on the left and down the right. It has flipped the whole graph like this. And we call it a reflection, and using mirror line y-axis or x equals 0. Either of those would work as your mirror line. Notice you've got to give a type of transformation, what the mirror line is, and then it will automatically give you your marks for understanding how it's been changed. If I wanted to flip it entirely the other way, it will look the same, which is a bit weird. But if I wanted to make it so like this goes down and this comes up, so it flips that way, I could use y equals minus x cubed. But hopefully there's a lot of people here who understand that that is minus x times minus x times minus x, which happens to be minus x cubed, which is the same as what we've just done there. So because they're the same, they both perform the reflection. But putting it in the brackets in general makes it flip up and down, not left and right. Just so happens in this example, it does much the same thing. Any questions? Okay, I can see I've got 10 or 11 people here. If you do have any questions, please look at the thing. I'm trying to check off people. That's how I knew that people couldn't see what I was doing. I do apologise for that. Hopefully I haven't driven too many of you to leave. This hopefully is making sense to people. So why am I teaching you this? Well, you need to be able to comment on what you think the transformation is. You also need to be able to do do a transformation to a thing. But this, I think, is the best use of this. And it's if I have y equals x squared plus 6x minus 3. We should have already learned, or some of you will already know, about completing the square. If I quickly do that, I look at the middle amount of x, 6x, and make it x plus 3 all squared minus 3. And then I take away 9 because it's take away that number squared. So I get y equals x plus 3, and forgive my bad x, but that's what the software wants. Y equals x plus 3 all squared minus 12. Let's see what that graph looks like. And hopefully you'll see something quite cool. And this is what I'm trying to teach you. This graph, this bottom bit, we should know by now that an x squared graph has one point of a stationary point, or a lower point, or a minimum point, and this point is at minus 3, minus 12. This completing the square, if we understand our transformations, tells us the minimum point on the graph. It tells us exactly where we can find the minimum point because we completed the square, and we are then able to see that inside the bracket it does the opposite to what you'd expect, it goes left, and outside the bracket it does what you'd expect, so this one goes down. Outside the bracket goes up and down, next to the x because it's doing it before you do the squared, it goes left and right, but the opposite way to you'd expect. So this is telling us that you can find the minimum point from a quadratic just by completing the square, using this idea of transforming graphs. Hopefully that makes sense to people. Let's do one more. I'll move down slightly, leaving the one above, and we've got y equals minus x squared minus 2x plus 4. So, first off, I'm going to complete the square. This is going to be easiest if I do minus x squared plus 2x minus 4. So it's going to make x plus 1 all squared minus 4 minus 1 is minus 5. But I need to do all of that times minus 1. So I'm going to give it minus x plus 1 all squared plus 5. Now, hopefully, we've got some people who are predicting already that a negative will have this shape. It will not have the upward shape we've been seeing so far. So, when I collect all this together, it does recognise it, so we can then plot in the graph, and we can see, if I insert this just over here, instead of a minimum, we now have a maximum, but the graph we've been using ourselves before, we've got this point here is the maximum, and we'll call it a maximum point, and it is the left one, and it is up 5. Well, that's what the up 5 has come from. How is this left one? Well, because in the bracket it goes the opposite way to you'd expect. The minus on the outside tells us the shape of the graph. Remember we talked about the reflection being the minus. What that minus has done there is it's flipped the whole thing upside down. So the minus has flipped everything upside down, and the brackets here tell us to go the opposite way, and up 5, and we can find the maximum and minimum points. The final thing I'm going to be doing today, for the last section, is when we are involving sine, cos and tan. Ordinarily, let's get a whole new page for this. Ordinarily, y equals sine x looks like this. I don't hold out much hope that it's going to read this, but we will see. No, it doesn't like it because I'm not being neat enough. Let's try that. And then circle it, and then turn to mouse, and it likes it. And we're going to zoom in a bit. And we're going to insert that. And we've got the sine curve. Now, any of you who are confused here by the fact that this has got 2 and 4, this means this is currently in something called radians that you learn at A level. Do not be put off by it. We can already see that this number here would be normally where our 90 degrees is. And this number here is where our 180 is. So we know it goes up to 1. I will investigate a little bit more with this software and see if I can actually change the parameters of the graph so you can have specific heights and depth and things. But look what happens with what we've learnt today of y equals sine x plus 5. We've already talked about, no, I didn't even do the x, did I? That sin plus 5 is going to do nothing, by the way. Sine x plus 5, what's it going to do? And what about y equals sine of x plus 5? What do we think they're going to do? Pause it. Have a draw. Have a sketch of what you think this graph is going to be. It does not need to be an accurate drawing. I'll show you each one in turn and see whether it goes with what you expected to see. First one has moved up 5 spaces. So it's gone from where it was up 5. It's taken the sine graph and moved the entire sine graph up 5. That's reasonable, right? This one, what do we think it's going to do? We are going to plot it, insert it. This one, I'm going to zoom in a bit so we can see what's going on. We should have here, we want to get rid of that one so it makes it nice and clear. The x plus 5, well, it's still the same height. This has still got a height of 1. Which, for those of you who've been following, hopefully should make sense to you. But what has changed is, this is not where that point is here. And the good thing about using radians is, it has actually moved left 5 places. This point is actually this point here that has moved all the way to there. Because it's moved 5 radians. Again, I'm hoping I can find a setting that will change it to degrees so we can show you the same things in degrees, but that shows you how we can use this with sine and cos. The final thing I taught you was y equals 2 cos x. But as I told you, if you've got a 2 outside, you will cause the whole graph to stretch. And I'm going to show you with a sketch what that would do. Normally we go up to 1. So let's go up to 2 now and down to minus 2. But the sine curve still will start at 0 because 2 lots of 0 is still 0. And at 90, 180, 270 and 360, it's going to go higher and back and lower and back. It will stretch that bit out and it will stretch that bit out. But it will keep these bits, which I did before, pin them to the line. Imagine putting a pin in and only stretching that to twice as high and that to twice as high. It's basically doubling both the height and the depth of this curve. apologies for the section where I was in front of the work. Hopefully that's made some sense. I will stay in the comments if any of you are stuck on any of this and need any more explanations. Hopefully this has been useful at both transforming graphs and then hopefully transforming trig graphs as well. I'm trying to work with you as much as you want. So anyone who's got any questions, please do ask. And that is me. The next thing I need to do is, I believe, fade to black, or I'll just fade.